Hello everyone, this is Samar Faris. In this video, I'll present our CVPR paper SPDMark Selective Parameter Displacement for Robust Video Watermarking. SPDMark is an n-generation watermarking method for video diffusion models. The main idea is to embed hidden frame-specific watermarks directly during generation by selectively modifying only a sparse subset of decoder parameters. Video diffusion models are becoming increasingly realistic and temporally coherent. This creates an important question. Once a video is generated and shared online, how can reliably verify where it came from? This is difficult because generated videos are often modified after sharing. They may be compressed, cropped, screen recorded, or encoded by online platforms. Unlike images, videos can also be temporally manipulated. Frames may be dropped, inserted, swapped, or trimmed. So a useful video watermark should be invisible, robust to common edits, temporally synchronized, and computationally efficient. Existing approaches face several limitations. Noise space methods embed the watermark into the diffusion noise and often require DDIM inversion during detection. This can be computationally expensive and fragile when the video is edited. Post hoc methods embed the watermark after the video has already been generated. These methods are useful, but they add extra latency and are disconnected from the generative process itself. Model fine-tuning methods modify the generator, but many of them use uniform modulation or fixed signatures. This limits their ability to support frame-specific messages and temporal tamper localization. So our goal is to build a watermarking method that is robust, efficient, and temporally aware. SPDMark starts from a base secret key. This key is expanded into frame-specific messages, so each generated frame receives its own hidden watermark. During generation, the video diffusion model uses selective parameter displacement to embed these messages directly into the generated frames. After the video is shared or edited, a verifier extracts messages from the received frames. These extracted messages are then matched against the expected sequence, allowing SPDMark to both detect the watermark and localize temporal edits. The key idea of SPDMark is that we do not modify the whole diffusion model. Most decoder parameters remain frozen. Only a sparse subset of decoder blocks is displaced. These selected blocks receive small low-rank basis shifts implemented using LoRa-style modules. This makes the watermark efficient. We only change a small part of the decoder while preserving the visual quality of the generated video. For each selected decoder layer, SPDMark learns a small dictionary of basis shifts. Instead of learning a new watermark model for every key, the system learns one reusable dictionary. A watermark key then selects one basis shifts in each layer, so different keys correspond to different sparse combinations of basis shifts. For videos, using one fixed watermark for the whole clip is not enough. SPDMark derives a different message for each frame from the same video level base key. Each frame therefore activates a different combination of basis shifts. This gives the video a temporal structure. At verification time, SPDMark uses a frame-wise extractor. The extractor processes each received frame independently and predicts the hidden message embedded in that frame. That gives us a sequence of recovered messages. However, if the video has been edited, this recovered sequence may no longer be aligned with the original frame order. If frames are dropped, inserted, or reordered, the extracted messages may be misaligned. SPDMark regenerates the expected frame messages from the base key and then compares them with the extracted messages. The matching is formulated as bipartite matching problem, where expected messages are matched to recovered messages based on bit similarity. Once we have this alignment, temporal edits become visible. If an expected message has no valid match, that indicates a dropped frame. If there is an extra recovered message, that indicates an inserted frame. If valid messages appear in the wrong order, that reveals frame swapping. During training, SPDMark jointly learns two components: the basis shifts used for watermark embedding and the frame-wise watermark extractor. The training objective balances three goals. First, message recovery. The extractor should recover the correct frame-wise watermark messages. Second, perceptible similarity. The watermark video should remain visually close to the original generated video. Third, temporal consistency. The watermark should not introduce flickering or unstable motion across frames. In our implementation, SPDMark is applied only to the decoder of the latent video diffusion model. We attach learned basis shifts to 14 spatial ResNet blocks in the decoder. Each block has 4 LoRa basis shifts, giving 2 bits per block and 28 bits per frame. For extraction, we use a frame-wise ResNet 50 model with a linear head that outputs the watermark message for each frame. We evaluate SPDMark on 2 video diffusion models. The first is SVDXT, an image-to-video model. The second is model scope, a text-to-video model. We evaluate video quality, watermark recovery, robustness under attacks, and temporal forensics. Here we compare SPDMark with the prior video watermarking methods. SPDMark achieves near-perfect watermark recovery, and at the same time it achieves the best subject consistency and motion smoothness among the compared methods. Next, we evaluate robustness across realistic attacks. These include compression, cropping, rotation, color changes, screen recording, temporal edits, and other post-processing operations. On average, SPDMark achieves the strongest robustness across attacks. Temporal localization is one of the main advantages of SPDMark. These results show that frame-specific messages allow SPDMark to accurately identify where temporal edits occurred. Here we show qualitative video results. The goal is to compare original generated videos with SPDMark watermarked videos. Visually, the videos remain nearly indistinguishable. To summarize, SPDMark is an efficient in-generation video watermarking method based on selective parameter displacement. It embeds watermarks by activating sparse combinations of learned low-rank basis shifts in the decoder. Overall, SPDMark provides a practical balance between visual quality, robustness, efficiency, and temporal forensics. Thank you for watching.